In this video, we will see the thermal aspect of chemical reaction. Two types of reactions are there, endothermic and exothermic. In exothermic, the heat is evolved, and in endothermic, heat is absorbed in the reaction. Any of chemical compound, when formed with its fundamental elements in its natural state, the heat evolved or absorbed in such type of reaction is known as heat of formation of that compound. Heat of formation of any chemical compound is also known as its absolute enthalpy value. It may be positive as well as it may be negative. Other heat of reactions are heat of combustion, heat of neutralization. Heat of combustion is always negative as energy is released in this process. Heat of neutralization means energy released during neutralization of acid-base reaction. Here given the two important laws of thermochemistry. First is Lavoisier and Laplace law. Second is the Hess law of constant heat summation. The Lavoisier-Laplace law states that if in forward reaction the heat released is Q, then if reaction proceeds in reverse direction, the heat of reaction is same Q but it is absorbed. According to Hess law, if a main reaction can be derived from the arithmetical operations of so many component reactions, then when we apply the same arithmetical operations on the heat of reaction of component chemical equations, we get the enthalpy of the main reaction. Suppose a reaction from A to B have heat value Q and a reaction B to C has heat value Q dash, then reaction A to C will have the heat value Q plus Q dash. In this video, we will learn the concept of bond energy. When bond is formed, the energy is released and it is an exothermic process. When bond is broken, the energy is required and it is absorbed by the bond, and hence it is an endothermic process. Thus we see bond formation energy is negative and bond dissociation energy is positive. Now as per standard definition, bond formation energy between two atoms A and B is defined as the energy released when A and B both in gaseous states combines and forms bond in between them. Here gaseous state of atom is very important. If in question it is given in solid state, then energy corresponding to state conversion we have to apply, as shown here in the example, where energy of sublimation of carbon solid atom is used. Here in this problem of Hess law, we have component reactions, the combustion of hydrogen, cyclohexane and cyclohexene. Their enthalpy values are also given. The main reaction is hydrogenation of cyclohexene. Our first task is to convert the subjective statement of the component reaction into chemical reactions and then try to find out by what means we can get the main reaction. Here, in this case, when we add the combustion of hydrogen and cyclohexane and subtract the combustion of cyclohexene with it, we get the hydrogenation of cyclohexene, and thus using Hess law we get the enthalpy of the final reaction. In the problem of Hess law given here, the component equations are heat of formation of water, heat of combustion of acetylene and heat of combustion of ethylene. When we convert this information into chemical reactions, we get set of three equations as shown here with their respective enthalpy values. Now the principal reaction is hydrogenation of acetylene. By inspection method, when we add chemical reaction 1 and 2 and subtract the chemical reaction 3, we get the principal reaction and its enthalpy values. Now this enthalpy is at constant pressure, which is higher by amount P delta V if the same reaction is carried out at constant volume. This at constant pressure, due to expansion, extra work P delta V have to be done. So we get the heat of reaction at constant value. Most of the substances on oxidation provide energy. A fuel is a substance which on oxidation provides sufficient energy which can utilize for practical work. The fuel value is defined as the energy released per unit weight or per unit volume of the fuel utilized. Here in the given thermochemical reaction, aluminium is oxidized and iron is reduced. During this process, energy is released. Here both aluminium and iron oxide is considered as a fuel, and the enthalpy involved in this reaction is 200 kilocalorie per mole. First we convert the 1 mole fuel in grams, then we can get the fuel value as kilocalorie per gram, and then using density value we can convert 1 mole of fuel in volume also and calculate fuel value as gram per cc. Here, methane is used as a fuel and we have to find out the fuel value per unit volume. The enthalpy value of combustion of methane will be heat of formation of water and carbon dioxide minus heat of formation of methane, and it comes as minus 801.8 kilojoule per mole. Now using gas law, we will find out the number of moles of methane in 1 meter cube volume at normal pressure and temperature, and this value comes as 40.93 moles. Hence, we can calculate the heat evolved during burning of 1 meter cube of methane by simply multiplying this number of moles into enthalpy value of combustion of methane. In the problem shown here, the total energy intake of the athlete will be 1560 kilojoule. Now 50% of this energy value he expended in the event, hence 780 kilojoule remained in his body. Since 1 mole water molecule needs 44 kilojoule energy for evaporation, hence with this energy, the number of moles of water molecule evaporated will be 780 divided by 44. Multiplying with molecular mass, we get the required weight. In the problem shown here, 3.67 liter of mixture of methane and ethene produces 6.11 liter of carbon dioxide. Suppose X liter of methane is there in the mixture, then 3.67 minus X liter ethene will be there in the mixture. Using mole concept, we get the volume of CO2 evolved as 7.94 minus X. When we equate this value to 6.11, we will get X value as 1.23 liters. Hence, we can get the volume percentage composition of the two gases. With help of volume percentage composition, we will get the volume of each component in 1 liter of gaseous mixture. Now using gas law, we can get the respective moles, and enthalpy value of both the species is given. Hence heat evolved by each component will be number of moles multiplied by its enthalpy value, and when we will sum, we will get the total heat evolved. Here in this question, the energy released during oxidation of 1 gram of carbon is given. Also, the energy absorbed during the reduction of cupric oxide weighted 3.975 gram is also given. So for enthalpy estimation, we have to find out the corresponding energy values per mole of the substance. These values comes as minus 110.52 kilojoule per mole for oxidation of carbon and 51.6 kilojoule per mole for reduction of cupric oxide. Using Hess law for the final reaction, the enthalpy value can be obtained by subtracting the enthalpy of the second reaction with the first one. Bond formation energy between two atoms is defined as the energy released during formation of that bond from its constituents atom in gaseous state. The heat of reaction in terms of bond energy is defined as the energy absorbed in breaking bonds in reactants plus energy released during formation of bond in product. Now here graphite is in solid state, hence heat of sublimation of carbon is also considered into picture for solving this problem. In the problem shown here, the heat of combustion of hydrogen, methane, ethane and carbon graphite is given. Also standard heat of formation of propane is given. All these 5 chemical processes is written in form of chemical reaction below. Now we need to find the heat of hydrogenation of propane. It can be found out with algebraic manipulation of given reaction. Further, we can implement the same algebraic calculations for heat values of the component reactions and find the enthalpy value of final reaction. In the given problem, we have to find out the heat of formation of HCl gas. The reaction is shown here. During the reaction, half moles of HH bond is broken, half moles of Cl-Cl bond is broken and 1 mole of HCl bond is formed. So enthalpy of the reaction is equal to the algebraic sum of the heat released during bond formation plus heat released during bond dissociation, and the value comes as minus 22 kcal per mole. In the problem shown here, the heat of combustion of ethane and propane is given here. Also, the heat of formation of water and carbon dioxide is also given. With help of these data, we can find out the heat of formation of ethane and propane as shown here. Now we can write down the chemical reaction for formation of both the species. It involves the sublimation of carbon and dissociation and formation of carbon-carbon, carbon-hydrogen and hydrogen-hydrogen bonds. Using enthalpy value of formation of ethane and propane, we can find out the required bond energy of CC and CH bond.
In this problem, we have to find out the bond energy of hydroxyl radical, that is OH gas, which is nothing but its formation reaction from oxygen gas atom and hydrogen gas atom. Now, this reaction can be obtained by given component reaction by arithmetic operations, and same arithmetic operation can be applied on enthalpy values of component reaction. So we get the enthalpy of formation of hydroxyl radical as minus 101.19 kcal, which represents the bond formation energy of single OH bond. Now it must be noted there, when in question it is asked about bond energy, it is bond dissociation energy. It is same as bond formation energy but with opposite sign. Hence OH bond energy will be plus 101.19 kcal.
In this problem, heat of formation of N2O is given. Now it should be noted here that N2O is a resonance stabilized molecule, and in the process of resonance, the extra energy from this molecule is released. The required reaction is written here, and its enthalpy value involves dissociation of 1 mole N triple bond N and half mole O double bond O, which requires energy to be absorbed. The exothermic part of the reaction is formation of 1 mole of N double bond N and 1 mole of N double bond O plus resonance stabilization energy. Hence, using the enthalpy value calculation, we get the resonance stabilization energy as minus 88 kilojoule.
In the problem shown here, we have to find out the enthalpy of combustion reaction of N-pentane, where various bond energies are given. It must be noted here that during combustion, the water molecule in product is in liquid form. Now, if you examine what process is happening during the reaction, it involves breaking of 4 CC bond, 12 CH bond and 8 O double bond O. In the reactant side and in product side, it involves formation of 10 C double bond O, 12 OH bond and condensation of 6 water vapor molecule into liquid form, plus resonance stabilization energy of 5 molecules of CO2. Here it must be noted, during water molecule formation, when 12 OH bond is formed, it gives the enthalpy of water molecule in gaseous form. Hence, energy released during condensation is also taken into consideration for enthalpy in liquid form.